The vector L can be easily computed by subtracting the light source position from a point. Similarly, the vector V can easily be computed by subtracting the position of the camera from the point. The only computation that requires a little bit of attention is the computation of the normal vector. Whether we use the Phong model or the Blin model, we need to determine the normal vector n at every point. But how do we find n in general? For simple surfaces like spheres, there are formulas, but how do we find n? The procedure will differ from representation to representation. In OpenGL, it is left to the programmer or the application to calculate the normals. Let's look at how to calculate the normal vector of a plane. This is the equation of a plane. From chapter 3, we know that the plane can also be represented by 3 points or a single point and a normal vector. Only a single plane can pass through a triangle or 3 points. The normal vector of this triangle or the plane, the associated plane, can be calculated by the cross product of two vectors in this plane. We can find the two vectors such as P2 minus P0 and P1 minus P0, and once we take their cross product, this will give us the normal vector. We would finally need to normalize the vector to unit magnitude. To define surfaces such as spheres, we have implicit representations. For example, here is a representation of a sphere with unit radius centered at the origin. So this is the radius of the sphere. The normal vector n at any point P is given by the gradient of this equation, which comes to 2x, 2y, 2z. Since x, y, z is a point P on this surface, the normal vector at any point P is equal to 2p. If we have a parametric representation of the same sphere in this form, x is equal to x of u v, where u and v are the two parameters, cos u sine v, and y is given by cos u cos v, and z is given by sine u. The normal vector at a point P is the normal vector of the tangent plane at that point. The tangent plane can be determined by the gradient of P with respect to u and the gradient of P with respect to v, given by these values. Finally, we can calculate the normal vector by taking the cross product of these two vectors. We can also compute the normal vectors of other simple surfaces such as quadrics or parametric polynomial surfaces such as Bezier surface patches given in chapter 10 of your textbook. However, in general, the 3D surface data generated by most scanners contain both vertex coordinates and vertex normals. And generally, you would represent 3D objects in graphics as triangular surfaces, and for every triangle you would use the process of calculating the normal of that plane to compute the normal of the triangular patch, and that normal would be ultimately interpolated to calculate the normal vector at every point on the surface.